Uh-huh. So, okay, let's get started. Uh, try to check your attendance on Blackboard. So as I mentioned in the first class, so I will check your attendance manually. You need to check your attendance on the Blackboard, okay? And then actually, during the first 2 weeks of this course, I will not count your attendance. So it is because actually the last a lot of this course can be changed during the first 2 weeks. So I will not check your attendance, but try to check your attendance system. Okay, it should work properly. So the weather is getting cooler. It's still humid. I don't like this weather. So anyway, so we need to start. Okay, so Uh, in the previous class, so I introduced about this course, okay, and then I explained why we need to study computer architecture, right? So in this time, I will explain about the abstraction of the computer system. So actually, you may know the terminology abstraction, or so you may think that this is so I don't know about the exact meaning of the word, the abstraction. So in Korean, the abstraction means 추상화. What does that mean? Abstraction or 추상화. So I remember that I explained the abstraction, the meaning of abstraction is that so we ignore some difficult part of our system. So because our target system can be very complex. Okay, so it means that it is difficult. It's difficult to understand the entire things of our target system. So in this case, we can just try to understand what is required for understanding. Okay, that is the meaning of abstraction. Okay, so let's see the analogy of abstraction. Okay, so you can find the very small cute girl here. Then what is she doing? She is driving, but it's illegal, maybe. So she is driving. So I believe some of you can drive, and some of you have a driving license. So then what is required for driving? So what should we know in order to drive a car? So we need to know how to use a handle, right? How to use pedals like the accelerator pedals and then or brake pedals, right? So actually, this is the analogy of abstraction of a car system. So in order to use a car, we just need to know about how to use handle, how to use some pedals, and then how to use some very basic functions of a car system. So I mentioned a system. So it is because actually the inside of a car includes the many complex parts, many complex components, such as the engines or brake systems. So these are mechanical systems, and then so actually we don't know. So we don't. So if we do not study about the car system, so we don't know. We don't know the exact mechanism or exact structure of is engine system or brake system of a car. But we can use a car system. We can drive a car. Why? So actually, in order to drive a car, you can just understand how to use handles or pedals or some basic functions. Then that's enough. we don't need to know about some detailed mechanism or detailed structure of our system. So actually, a car is a very complex system. So this is the analogy of abstraction. Even though the system is very complex, okay? So it's see, but we don't need to understand the entire things of this target system. Okay, we can just know some reveal some interface. So we can just understand some small portion of required knowledge about the car. Okay, so this is the abstraction layer. Even though the detailed system or detailed structure of a car is very complex, we can actually a small part like handle, pedal, and then some functions. These are called interface. So we can just understand some functions or interfaces of a system, and that's it. So we can use the target system, or we can understand the target system in an abstraction level. Okay, so this is another analogy of a vending machine. So in order to use the vending machine, we can just push some buttons. Okay, so it's very simple, but inside of the vending machine, you can find a system. Right? So actually, this vending machine may have a processor like computer, a processor, and then some I/O systems. But you don't need to know. You don't need about the inside of the vending machine not to use the vending machine. So this is the meaning of abstraction. Also, this slide shows the various levels of abstraction level, the various layers of computer systems. Okay? So, as I mentioned, the meaning of abstraction is that the hiding details when they aren't important. Okay, so aren't important. So it means that in order to use or in order to study a certain layer of complex system. So actually, we are learning about the computer system. So in order to study a certain layer of a computer system, we can just ignore some not important things, okay, not important concept. So for example, so these are layers, layers of a computer system. So if you see this figure, so you can find so in order to understand the entire things of computer systems, then so you may think, oh, we need to understand the physics. We need to understand the device level knowledge, such as the transistors or diode. Also, actually, inside of the computer system, all signals are analog signals, right? So actually, our world is analog world, not digital world. But we can understand the computer system like the digital manner. But actually, so the circuits inside of the computer system are actually analog circuits. Okay, like the amplifier or filters and some logic gates. So actually, these circuits works in an analog manner. But also, we need to understand the data circuits, logic, and some architectures. And then actually, in order to run on some applications on the computer systems, we require operating systems, right? Like the Windows, Linux, or Mac OS. So we require operating system. And then on the operating systems, you can just run applications like the internet browser, office programs, or some game application, and so on. So actually, we are here. Humans are here. So human. And then actually we are interfacing with computer system through the application layer, right? We just interface with the application layer only. But under this application layer, so we can just find the many different level of layers in the computer system. And it's not easy to understand some entire things, entire knowledge under the computer system. Okay, so it's very complex. So maybe we can learn about some basic physics or some knowledge on electric devices, but actually we do not understand uh, thoroughly. Okay? So as a computer engineering students, then we can just focus on a certain layers of computer systems. So if we take some other courses, then these courses also focus on a certain layer of a computer system. So if you took the digital logic system, so digital logic system focuses on the logic level and then digital circuit level of computer system. Okay, and then in this course is the COSE222. Okay, so computer architecture course so focuses on the architecture level and then micro architecture level of computer system. Okay, but in an abstraction level. Okay, so it means I will not explain about some detailed logic level or detailed digital circuit level of computer system. We just focus on this level. Okay, some details are ignored, like the digital logic or digital circuits. So this knowledge will not be taught in this course. Okay, we just focus on the certain level. So it's because this is how we understand some complex systems. So like these analogies, if a system, target system is very complex, we don't need, but we want to use the target systems, right? But we don't need to understand the entire things. Just simplify. We just simplify the target system and then only the required interfaces like the handle, right? So these are kind of interfaces to the car system, right? So if we just push some acceleration pedals, then the engine works. Okay, and then if we just push it brake pedals, then brake system works, right? It's just interface. We can just understand the interface of a system. It's the same. So there are many layers under the computer system, and then so let us assume that we just focus on the architecture level of computer system. Then we can just understand some output signals or interface signals from microarchitecture level. And then we can generate some required signals or required information to the upper level, like the operating system. Then if we just study operating systems, we just ignore this underneath layer analysis, and then we can just understand the interface between operating system level and architecture level. Okay, then we can just write operating system code. Okay, so that's how we understand the complex system. So we just divide the target complex system into many layers, and then we just focus on a certain layer only. Okay, but and then so detailed analysis of the underneath layer is can be ignored. Okay, so in this course, so as I mentioned, so we will focus on these levels, architecture level and microarchitecture level. Okay, and then this part can be explained. Okay, so so actually, so in order to build, a computer system, actually, anti-analysis is required. So it means many engineers are working for building a computer system, right? It's a very big industry, right? But and then also the system is very complex, but it just focus on a certain level of a system. Okay, so this is the meaning of abstraction. And then actually this concept, the abstraction concept is very important in computer engineering study or computer science study. Okay. Okay. So we actually, if you actually this is the sophomore level course. Okay, so it's kind of a fundamental level course, right? So, but if you become a junior level or a senior level students, then you will also focus on some different levels of computer systems, such as the application level, operating system, or some system level, also architecture level. Then we can just focus on the analysis on a certain level only. Okay, but it's very deeply. Okay, so but this abstraction concept is very important. So also the abstraction means that providing only required interface information, as I mentioned. So we can just understand the interface signals or interface information between two adjacent layers. Okay. Okay, so let's see the example of abstraction level on a processor. What is this? So you can find a title of this slide inside of a processor. So this is a photo of the Intel CPU die. Die. Okay, so die means actually die represent a surface of a chip. Okay, chip. So this is a very beautiful photo, right? So and then what can we understand? What can we understand if we see this photo of Intel CPU die? So it means that what is the information we can get from this photo? So actually nothing, right? So if we just see that this photo, oh, it's beautiful. And then, oh, I don't, what? That's it. We cannot get any information, but we cannot get any knowledge from this photo. But how about this? So what is included in this photo? So I just so you can find that, or actually you can find some part in this Intel CPU die, and then also you can find some different components. Different components on this is for for Intel CPU die. So if you see this figure, then you can find, oh, this is the memory controller, so which means that this Intel CPU will interface via this memory controller to the external memory for this part. Okay, and then for these CPU cores, so we can know, oh, this Intel CPU includes 4 cores. It's a multi-core architecture, right? And then, so you can find the L3 cache and then interconnect. The 4 cores and then L3 cache are connected via interconnection network for this part. So you can find the L3 caches here. And then you can also find, oh, this Intel CPU has GPU, the graphical processing unit, a graphics processing unit. So GPU includes the this amount of auto die. Okay, so this is the example of an abstraction level. So actually, we don't know about we cannot get any information from this photo, but we can get some information from this figure. Okay, but details are hiding. It means actually it's low. So actually there are many registers. Okay, we can observe many transistors in this forum, because usually the recent Intel CPU chip includes billions of transistors, right? So very small, so we cannot observe it, but there are billions of transistors. But in this, so this is the abstraction level. So I did not explain about this transistor level information. Okay? Also, some detailed architecture level is also hidden. Okay. I just explained a certain level. It's simplified. Okay. It's simplified. A certain information is hidden, and then so only required information is revealed by this abstraction level. Okay. Also, okay, what can you see? This is the another abstraction level of a CPU architecture. So it's different. So in this, why is this so long? So in this slide, you can just find a very brief structure or brief abstraction level of Intel CPU, but you can find complex diagram, and then some data flows like these arrows represent data flows between different components. Okay, so you don't need to understand this because but it's just the example of different abstraction level of processor architecture. It's different, right? So this abstraction level and then this abstraction level is different. It's a more detailed architectural level of Intel CPU core. I mentioned core. So actually, so this is the CPU core, and then actually inside of this CPU, you can find many components. So actually the CPUs are very complex. Okay, so you can observe many different components, and then these many different components are connected to each other, and then data flows between components. Okay, so it's a different abstraction level. So actually, if you see that this figure, this information is hidden, but actually, yeah, in this architectural view, so we can understand the detailed information regarding architecture of individual Intel CPU core. Okay. But if we also see that this figure, so you can just find a certain rocks like the instruction TLB, like the fetch, and then decode. But also some detailed information is hidden here. So in order to build each component, actually each component includes the many different types of logic gate or functional blocks. But this level is also hidden. Okay, we just focus on the certain abstraction level. That's how we understand some complex systems. Okay. Okay. So this is some example of abstraction, and then also I hope we can understand the concept of abstraction in computer science or computer engineering on the computer systems. Okay. Okay. So let's see some basic information or basic components or basic layers of our computer systems. So you can find, this is the below your program. So actually, as I mentioned, we interface with application level. So application is actually program. Okay. So, but below this application level, we can find so many different layers. Okay. So actually, because these layers are hidden, we just interface with the application layer, right? So it means we just understand what we see, but actually under the some layers, so we need to. It's not easy so sometimes because we just see some outer layer of a system. Okay, but as a computer engineering student, you need to understand some underneath layers, detailed mechanism or detailed structure of a computer system. Okay, so application software. So I believe you are familiar with programming languages because I believe you just you took some programming language courses. Okay, the basic courses in computer engineering department. So if we just make a program, well, if we just want to make an application, we write a code. We write a code in Python, C, Java, some other languages such as Go, Swift, some other language, and then also recently some other languages, Rust. Okay, so actually Rust is popular, is getting popular. Okay, but so you know, so if we write a code in Python or C, syntaxes of these languages, program languages, are similar to our natural languages. Right. So like if you see the function name or syntaxes like the some for or not in Python, maybe while. So actually you can find that the syntaxes in high-level languages are similar to our natural languages. So which means we can understand. We can easily understand the the co- the program code. The program code written in is high level languages. Okay, because these program languages are similar to our natural languages. But so if you took the this is the largest system, then you can, I believe you know the computer system is a kind of digital systems, right? Which means a computer system, well, a computer processor can only understand digital signals, right? What does that mean? Data signals is a discrete electric signal. It's composed of 0 and 1. So 0 means low voltage signal, and then 1 means high voltage signal. Okay? Actually, our computer system can understand digital signals. Okay, 0 and 1. So then what is required? Translation is required. Okay, so we write a code in high-level languages, but our computer system or our processor can only understand the digital signals 0 and 1. What is required? Translation. Okay, obviously. So you can find, so under this application software layer, you can find system software. And then actually these are two representative system software, compilers and operating systems. So compilers and operating systems are two representative system software. So what's compiler? Compiler translates high-level language code. So high level, so like C, but like Python is different because Python is the interpreter based. So compiler translates high-level language code to machine code. So we will learn about the machine code in this course. Okay, so but a processor can understand only machine code, not high-level language code. So translation is required. Actually, compiler translates the high-level language code into machine code. Okay, and then operating system. So operating system interfaces with hardware. Okay, so architecture level. So operating systems manage the hardware component or hardware operation, and then operating system launch or execute our programs. Like a binary code some process. Okay, so these are actually main role of operating system. So recently, so the operating systems are very fancy. So which means that we just use operating systems via graphical user interfaces like GUI, right? It's very fancy and then it's very convenient. So we just understand that Mac operating system or Windows, Linux operating system, you know, so like it's a kind of graphical interfaces, but actually the main role of operating system is to manage hardware, like managing computer systems, also the managing the processes, like the launched or executed binary files. Okay, so these are main roles of operating system. The GUI is the kind of some interface to the user. Okay. We can find the handling the operating system handles input and output. Like the input and output means that it's a keyboard, mice, storage system like SSD or hard disk drive, and then it manages memory and storage. Okay, and then it schedules tasks and then sharing resources. So this is the main part of the our computer system. Okay, and hardware. So under the operating system, there is hardware, and hardware is represent includes the processors like CPU, the memory like DRAM, then I/O controllers. So we also use the keyboard, mice. Then actually these helpers, I/O helpers, needs to be connected to the CPU. Okay. So this slide shows the levels of program code. So it shows how high-level language code is translated into the machine code. Okay. So I just mentioned a compiler that translates high-level language code into machine code, but actually the compiler translates the high-level language code to the assembly code. And then assembler translates this assembly code into the binary code, this machine code. Okay. So, but usually we just mention these compilers and the assemblers are compiler. Okay. So if we take the compiler course, then it's a this part is called the front end, and then this part is the back end. Okay. Anyway, so actually the meaning is a little bit different, but usually. Okay, so firstly, so this is the high-level language code written in C. Okay, you can find the familiar syntaxes and then function names here. And then compiler just translate this high-level language code into the assembly code. And what is our assembly code? So actually, this is the same code. It's a swap function, and the function is compiled. Then compiler, sorry, compiler generate is assembly code. So you can find some unfamiliar lines here. So, and then this code is translated the machine code actually. So you can find the RISC-V and RISC-V. So a processor can only understand this type of data, this type of signals, 0 and 1. It's a digital signal, right? So, but our processor just find instruction set architecture. So you can find some words here. Okay. So actually, these are instructions. Okay, so these, so SLLI, add, LD, so load double word, then JLR. So these words represent abstraction, instructions defined by instruction set architecture. So actually defined by instruction set architecture of RISC-V. Because in this course, we will learn about the RISC-V ISA. Okay. So, and then actually, these one line of assembly code is translated into the one line of machine code, one to one. So because this is the RISC type instructions. Okay. So the compiler. So if you see that this assembly code, so it's a little bit familiar. It is because the assembly code so use assembly code uses alphabets and numbers. Okay, right? So it's not familiar. So you are not. I believe most of you are not familiar with assembly instructions, but because we can just use the high-level language. But anyway, we can, if you learn in this course, then you can understand. You can understand the meaning. The meaning of is lines of assembly code. Okay, because instruction and then some numbers, and then these instructions are actually defined in ISA instruction set architecture. Okay, so compiler generate the assembly code. Assembly codes include instructions defined in ISA instruction set architecture. And then is assembly code is translated into machine code. So these are levels of program code. So actually our program is translated and then machine code. This binary code is executed by processor. Okay? These binary codes are executed in a computer system, actually. Okay. So I hope you can understand these some compilation processes. Okay. So then I also mentioned that Python is different because Python is the interpreter-based language, not compiler-based language. C, Java, and then some other languages. So compiler-based languages, but Python is different. Even though the Python is very easy to learn, but Python is the interpreter-based language. So it's executed line by line with Python. It's different. But usually compiler-based language is best. So even though the Python is easy to learn, but Python is so slow, very slow. Okay, this is how the program is compiled and then how the program is executed. So our computer system includes the many different components such as the user interfaces or storage, and then IO, the network, and then some IO devices. Okay, so actually it's all complex. So what is this? So this is the photo of main board, computer main board. So actually, so recently our computer system is very fancy and then very small, right? So it's not easy to see some inside of our computers, right? So we usually use laptops, and then it's very light, and then it's very small, and then but So if we use a desktop computer, then we can observe a very large board. And then on this board, many components are assembled. Okay, so actually this slide shows a photo of main board of a desktop computer. It's a little bit old, but you can also find the many different components. So actually, if you so you are learning about a computer system or computer hardware, then I hope you can understand some basic organization, a basic organization of this computer system. So actually, you can find the socket here. So CPU will be assembled here, and then CPU is connected to the memory. So this memory is called the external memory, and then we use the RAM as a main memory of a computer system. So actually, DRAM modules are connected to this memory socket. Also, then what are other parts? Other parts are I/O devices. Okay, so it's not easy to understand with the photo. So we can understand a computer system like this abstraction level. So this is also another abstraction level. It's a diagram. So, but you can find that this is the computer system architecture and right, old. So this is the old generation computer system organization. So what can you observe? So now, so you need to practice how to understand this system using diagram. Okay, like this. So this is some example of abstraction level. So you can find CPU. So CPU is the main part of the computer system, right? So it is similar to our brain in our human body. So, and then you can find that CPU is connected to the memory. So this is the external memory or main memory. Then I said that we use the RAM as our main memory. Okay. And what can you observe? CPU is connected to the main memory via memory bus. Okay. So, and then also you can find that this memory bus is thicker than other lines. So which means it means the bandwidth is high. Okay. So it is because the CPU frequently interface with external memory, main memory. See? So bandwidth is very high. You can find the GPU is also connected, but another is memory bus. And then you can find the other I/O devices or other peripherals are connected. So this is some main rule. So CPU is very fast, so it's a fast. And then also memory is fast, but it's slower than CPU. But CPU is fast, and then CPU is the most important part in our computer system. So, and then in the old generation, in the old computer system, the GPU is a kind of peripherals, and then the GPU is slower than the CPU. And then usually these I/O devices like keyboard, mice, or network, and then some storages. These devices are slow, very, very slow. Okay, so fast and slow. What can you observe? Oh, fast components are located in the upper part, then slow components are located in the lower part. So it is hierarchically organized. Okay. This is also the main approach of a computer system. If we require a faster component, this component is directly connected to the CPU. Okay. Then if some components are very, very slow and then it's infrequently used, then these components are connected to the CPU, but the bandwidth is very low, and then it's located in the lower level of the hierarchy. Okay, this is the main approach. So and then this is the recent computer system. So then you can find that it's similar, but this part is different. GPU is directly connected to CPU. So it is because also you can find that this bus. So this interconnection is very thick. It means we require high bandwidth between CPU and GPU. So it's different. So it's a recent computer system organization. And then also this is some detailed organization of a computer system. Okay? But you can understand how the computer system components are organized. The CPU is the main part. Okay, so it's the CPU, and then CPU is connected to the mainboard chipset, and then mainboard chipset manages the communication with the other slow components. Also, you can find that GPU and then main memories are directly connected. Okay, because we require high performance to GPU or memories. Then slow components are connected to the mainboard chipset, the hierarchically. Then because these are slow. That's how our computer system is organized. And then this is the somewhat different abstraction level, so some high level of a computer system. Okay, so this is the some example, some concept of a certain abstraction level of a computer system. Okay. So now, I will explain some technology. So semiconductor technology for building processors. Okay. So I mentioned that okay, so let's see this figure. So this is the die photo of Intel CPU. And then I mentioned that there are many transistors. So actually we use semiconductor technology to build a CPU or some other processors, right? So I know it's not easy to see some main board of our computer system, but if you see the main board of a computer system, you can find a chip, right? So here is a chip. You can find like this. Okay, this is the CPU chip, right? And then under this package, so actually these are, so you can find some lead. Okay, so under this packaging, so you can find actually if you just open the packaging, then you can find some this figure, the diagram of a CPU. But and then inside of the CPU, there are many transistors. And then these transistors are built using semiconductor technology. Okay. So actually, the semiconductor technology is critical. It's critical for the computer system, the performance of computer system, right? So, so recently, semiconductor technology is very critical, right? So, the US, United States, the prohibit some what's that? The ASMR, some semiconductor manufacturing devices. So the US prohibit the purchase of some semiconductor, so advanced semiconductor manufacturing devices to China, right? So semiconductor technology is so important. It's also critical. Then it's also critical. It is because it's critical for the performance and then the performance of a computer system, or the performance of CPU, or performance of memory. Okay. So I briefly explain some basic. So actually, we will not. So as I mentioned, we will just focus on the architectural level of a computer system. So we will not learn about the semiconductor technology, but I briefly explain. So this slide shows the DRAM capacity by years. So x-axis is the years, and then what is the y-axis? Y-axis is the capacity of the RAM. So what can you observe? So we can observe the capacity of the RAM is increased by year, right? So this is the time, and then this is the capacity. But also you can find that this y-axis is the log scale, and then this is linear. So what does that mean? The capacity of the RAM has been increased exponentially. Okay, actually this is linear, but this is the log scale. So actually, the capacity is increased exponentially. What does that mean? How? How is this possible? So, so actually DRAM is composed of like this. Actually, this is the transistor. Okay. This can be possible because the transistor size is reduced. Okay. So basic component. So actually, we can build our processors or memory using transistors, right? And then the size is increased, which means this basic component, transistor size is shrinked dramatically. Okay, so which means so you can find the TSMC is is using 5 nanometer technology, and then Intel is struggling recently. So Intel is using 10 nanometer technology. Actually, this number 10 nanometer or 5 nanometer represent the size of a transistor. So if we use a smaller transistor, then we can include in the same area. Sorry. If we use a smaller transistors, and in the same area, we can include more transistors. Obviously, right? So which means we can make better devices, like better memory or better processors. Okay, that's why this number is important, is critical. Okay, So that's why, so recently Intel is struggling. So Intel is using 10 nanometer technology, and then other processor vendors such as AMD or NVIDIA, also Samsung, is using 5 nanometer or 3 nanometer technology. It's smaller. So if we make a smaller transistors, and in the same area, we can include more transistors, which means the performance. The capacity is increased in the memory, also the performance can be also increased. Okay. So this slide shows the advancement in semiconductor technology. So actually, the first computer was built using vacuum tube. Okay. The first computer, such as ENIAC, was built using vacuum tube, and then you can find that relative performance per cost. So vacuum tube is 1, then transistor is 35, and then the 2013. So you can find that the relative performance per cost is very high. So the semiconductor technology has been advanced dramatically. Okay, which means we can use better computers. We can use higher performance in our computer system. Our computer systems become higher performance. Okay, so this is the brief process of semiconductor manufacturing. Okay, so so actually, our processor, like the semiconductor devices, are manufactured using silicon. So silicon is the main material, for semiconductors. Okay, so firstly, we use the very pure silicon cylinders, and then this cylinder is called the silicon inductor. Okay, and then we slice silicon cylinders to the wafer. And then on the wafer, we manufacture the dies. So dies. So it means the individual chip. Okay. So actually, the final shape of the chip look like this. But inside of this packaging, inside of this chip, you can find a die. Okay, it's a die. And then actually these dies are manufactured the silicon wafer. Okay, it is called fabrication. So actually dies are fabricated silicon wafer. Okay, so like this, and then so this is the figure of the Intel Core i7 wafer. So you can find that many rectangular form. So these are individual die. It's a die, and then we fabricate that multiple dies, silicon wafer. Okay, so but during the manufacturing, some effects can be included, like the cause of dust or some process variation. Some defects can be included, and then we cannot use defective chips, defective dies. So we test the dies, and then defective dies are removed. Okay, like this. You test the dies, and then some defective dies are just thrown away. And then it's a package using the package processing, and we can make the chip. Okay, so this is the Intel i7 wafer, as I mentioned. So this is the 300 millimeter wafer. So diameter, it means that the diameter is 300 millimeter. And then we can find the 280 chips. Okay, 280 dies. And then we use this in this figure. The semiconductor technology node is 32 nanometer. Okay, so I mentioned that this number represents the size of transistor. Okay, how about this? Intel Core 10th generation. The wafer size is the same. It's a 300 millimeter. But how many chips? 500 chips. Why? Technology 10 nanometer technology. Okay, the size is reduced. So in the same area, we can make more chips. And then also the performance is improved. Okay. So also the cost per die is, so actually the cost is important because, right? The cost is also important. So we are engineers, right? So actually two goals of engineering is performance and cost. We need to increase the performance, but we need to reduce the cost. Okay? These are two main targets of engineering. Okay? So you can find that the cost per die is the cost per wafer divided by dies per wafer multiplied by yield. So yield means that it's a kind of some defection rate. Okay, so and then actually the yield is inversely proportional to the area. Okay, so smaller chip is usually the smaller chip exhibit the higher yield. Okay, so this is just some common sense. Some basic information about some semiconductor manufacturing. Okay, so you can just understand that if we use the smaller transistors, then some advanced semiconductor technology, then we can build better processors, what? Better memory. Okay. Okay. So now, so in chapter 1, so we will discuss about the performance, so how to measure the performance of a computer system. Okay. And then I will briefly show the analysis. That's just the analysis of performance of some performance of a certain system. And then in the next class, we will learn about the performance. This is just the analysis. So I will quickly show the analysis of performance. So I think so this slide shows the performance of airplane. Then how can we measure the performance? So which means, oh, this airplane is better than that airplane. How can you say? So actually, we can use many different performance metrics. What does that mean? So we can say that, oh, this airplane is better than that because this airplane can include more people. The capacity, which means the capacity is higher. Also, we can say that, oh, this airplane is better because speed is higher. So what does it mean? We can say that, oh, this system is better than other systems because different performance metrics. We can just focus on the capacity. We can just focus on the speed. We can just focus on the some combined capacity and speed. Okay, so this is the example. So the passenger capacity, oh, A300 is the best, but cruise range is some execution time, no, the running time. So Boeing 777 is the best, and then speed, oh, Concorde is the best. So it means, so we can use different metrics to measure the performance of a system. It's the same. It's the same to computer system. Actually, understanding the performance of a certain system is very important because, as I mentioned, we are engineers, and then our goal is to increase the performance. Then how? Then how can we measure? How can we compare the performance of our system with the performance of other systems? So we need to know some performance metrics. Okay. In the next class, we will learn about the performance metrics and how to measure the performance of our computer system. But you need to understand that we can use different metrics for different purposes of our system. Okay. Okay, so I will stop here. Any questions? Okay. Thank you for your attention, and then see you in the next class.